Welcome to the Deep Dive. Today we're diving into the world of quantum machine learning. Specifically, we'll be exploring a scientific review article on tensor networks for quantum machine learning.
Sounds exciting.
It is. I'm really curious to see how quantum computers could change machine learning as we know it. Where should we start?
Well, to start things off, it's amazing how a tool originally designed for quantum physics is now finding new applications in machine learning.
That is interesting. Could you elaborate on that?
Yeah, sure. You see, tensor networks are all about breaking down really complex things. Imagine you're trying to analyze a huge data set, like a high-res image.
Yeah.
It's like trying to solve a gigantic jigsaw puzzle with like millions of pieces.
Oh, I see what you mean.
It can get really overwhelming, right? But tensor networks offer a really elegant solution. They let us break down that massive puzzle into smaller, interconnected pieces that are much easier to work with. It's like breaking down that million-piece puzzle into more manageable chunks.
Yeah.
Makes it much less daunting.
So instead of trying to analyze the entire sea of data, we can focus on understanding the connections between those smaller pieces.
Exactly. Each of those smaller pieces is called a tensor, and they're connected in a specific way to create a network.
And how they're connected matters, right?
Absolutely. The way those tensors are arranged depends on the type of data you're working with and the task at hand. Some layouts are linear, like a chain of tensors, while others are hierarchical, like a tree with branches. Each layout has its own advantages and disadvantages, making it suitable for certain types of data.
So we've got these different tensor network layouts. Are there any that are particularly important for quantum machine learning?
Definitely. Two great examples are the matrix product state, or MPS, and the tree tensor network, or TTN for short.
Okay.
The MPS layout is like a line of tensors, which is perfect for 1D data like time series.
I see.
On the other hand, the TTN, with its branching structure, is well suited for more complex, multidimensional data like images.
Okay, so we've got these tensor networks. They can break down complex data, and there are different layouts for different tasks. But how are they actually used in machine learning? Let's start with classical machine learning, the kind we use today. How are tensor networks making a difference there?
Well, they're being used for all sorts of things, from image classification to data compression. For example, imagine trying to train a computer to recognize different objects in an image.
Something we take for granted with our smartphones these days.
Right. But behind the scenes, it's computationally very intensive. Tensor networks can help make this process more efficient by representing those objects' features in a very clever way.
Yeah.
It's like giving the computer a more organized way to see and understand those objects.
Interesting. So they're not just breaking down data, but they're also helping computers learn from that data more effectively.
Exactly. And they can even create what are called generative models, which learn the underlying patterns in data and then generate new similar data.
So they can be used to create things like realistic images or even compose music.
You got it. They're incredibly versatile tools. But where things get really interesting is when we bring these tensor networks into the quantum computing world.
Okay, now we're entering the mind-bending world of quantum mechanics, right?
That's right. And the structure of tensor networks makes them perfectly suited for quantum computers. It's like they were made for each other.
How so? Can you explain that a bit more?
Sure. So those tensor nodes, those individual pieces of a tensor network, can be represented by quantum gates. And the bonds that connect those nodes, well, those can be represented by qubits, the quantum bits that carry information in a quantum computer.
Okay, so we're taking the building blocks of a tensor network and translating them into the language of quantum computers using quantum gates and qubits.
Precisely. And when you do that, you create what are called Quantum Tensor Network Machine Learning Models, or QTNML for short.
QTN-ML. Oh, that sounds powerful, but how does it actually work?
Well, these QTN-ML models operate in the unique realm of quantum mechanics. They harness these strange properties of superposition and entanglement to perform calculations in a fundamentally different way than classical computers.
I've heard about superposition and entanglement. That's where things can be in multiple states at once and connected in spooky ways, right?
Exactly. And those quantum phenomena give QTN-ML models a huge advantage. They can explore a vast space of possibilities all at the same time, potentially finding solutions that classical computers could never find.
So it's like they're searching through a multidimensional maze, taking all possible paths at the same time. That's incredible. But there must be some challenges in actually building and running these QT and ML models, right?
You're absolutely right. Building QT&ML models often requires creating large, complex quantum circuits, which are really difficult to implement on the quantum computers we have now.
Because quantum computers are still in their early stages of development, right?
Exactly. They're like the first computers ever built, bulky and error-prone. So it's really challenging to get these sophisticated QT&ML models to work on this limited hardware.
So what are researchers doing to overcome these challenges? Are there any clever workarounds they're using?
Researchers are getting creative. They're coming up with some pretty neat strategies to simplify these really complex quantum circuits and make them more manageable for the quantum computers we have today.
Can you give me an example? What kind of strategies are we talking about?
One approach is to break down these complicated quantum operations into smaller, more manageable steps. It's kind of like building a complex machine from smaller modular parts.
Makes sense. And I imagine that would make things easier on those early stage quantum computers.
Exactly. Take some of the pressure off. And another thing researchers are doing is they're designing what they call qubit-efficient layouts for their tensor networks.
Quite efficient. What does that mean?
Well, remember how we talked about the different layouts for tensor networks? Some layouts use qubits more efficiently than others. For example, the matrix product state layout, that line of tensors we discussed earlier, is particularly good for certain types of data and doesn't need as many qubits as other layouts.
So by choosing the right layout, they can make their QT and ML models run more smoothly on these limited quantum computers.
Exactly. It's all about making the most of what we have. And there's another technique that's becoming more and more popular, hybrid training.
Right. We touched on that earlier. It's combining classical and quantum computation, right?
Exactly. It's like having a team of experts working together. Each one brings their own unique skills to the table.
I like that analogy. So how does this hybrid training work in practice?
Well, imagine you start by training a simple version of your QTN ML model on a classical computer. This gives you a good foundation, a set of initial parameters that are already pretty good. Then you transfer this pre-trained model to a quantum computer.
So you're giving the quantum computer a head start.
Exactly. And then the quantum computer can use its special abilities to refine those parameters, maybe reaching a level of accuracy that classical computation alone couldn't achieve.
So even though quantum computers are still pretty young, researchers are finding some really clever ways to use their power. It's like squeezing every ounce of performance out of these machines.
It really is. It shows how resourceful and dedicated they are to pushing the limits of what's possible.
It's exciting to see how this field is progressing. But I'm curious about the real-world applications of QTN-ML. What are some actual problems these models could help us solve?
Well, let's think about something that affects all of us. Healthcare. Imagine using QT-NML models to personalize medicine, tailoring it to each person's genes and lifestyle.
That would be incredible.
Right.
No more one-size-fits-all treatment.
Exactly. These QT-NML models could look at tons of data, from your DNA to your medical history, to figure out the most effective treatment for you.
Wow. It's like having a virtual doctor that knows you better than you know yourself. Are there any other areas that could benefit from this technology?
Oh, absolutely. Another area that could be revolutionized is materials science. QTN-ML could help design new materials with properties we can only dream of.
Like what? Give me an example.
Imagine materials lighter than steel but stronger than diamond, or materials that can conduct electricity with zero resistance at room temperature.
Now, that sounds like something out of a sci-fi movie, but could those actually be possible?
They might be. And QTN-ML models could help us get there. They could help us simulate how atoms and molecules behave, allowing us to explore a huge number of possible material combinations and pinpoint the ones most likely to have the properties we want.
So it's like having a quantum chemist working with material scientists to create the materials of the future.
Precisely. And it doesn't stop there. Healthcare and material science are just the beginning. QTN-ML could be used to improve all kinds of complex systems, like managing traffic in a city or distributing energy across a power grid.
So we could have smarter cities and more efficient energy systems.
Absolutely. And that's just scratching the surface. The possibilities are truly endless.
It's amazing to think about the impact this technology could have on our world. It feels like we're at the start of a new era, where quantum computers and machine learning join forces to tackle some of our toughest challenges.
We are, and it's important to keep in mind that we're still on this journey. There's still a lot we don't know about QTN-ML, and there are plenty of challenges ahead. But the progress we've made is truly remarkable, and the future looks incredibly promising.
I'm eager to hear more about the progress being made. What are some of the most exciting things happening in QTNML research right now? What kind of breakthroughs are researchers making?
Oh, there's a ton of exciting stuff happening. One really cool area is developing more efficient and scalable QTNML algorithms. Remember, we're still working with those NISQ devices, noisy intermediate scale quantum computers.
Right, those NISQ devices still have a way to go before we get those large-scale, fault-tolerant quantum computers of the future.
Exactly. So researchers are figuring out clever ways to make QTNML models work well on these NISQ devices, squeezing out as much performance as they can.
And one of those strategies is using these hybrid algorithms, right? Combining the strengths of both classical and quantum computing.
That's right. We talked about hybrid training before, where you pre-train a model on a classical computer and then fine-tune it on a quantum computer. But researchers are exploring other ways to build these hybrid models, too.
Like what? What are some of those other approaches?
Well, one interesting idea is to use classical computation for pre-processing and post-processing the data. It's like prepping the ingredients and setting the table before the quantum chef gets to work.
So the classical computer would handle things like cleaning the data, simplifying it, or even correcting errors after the quantum computation is done.
Exactly. By taking care of some of those tasks on classical computers, we can make QTN ML models more efficient and less prone to errors, even with those early quantum computers.
It's amazing how researchers are constantly pushing the limits of what's possible with the technology we have. But have there been any real breakthroughs? Has anyone actually built a QTNML model that can solve a real-world problem?
There have been some really impressive breakthroughs lately. One that comes to mind is the development of a quantum image classifier that uses a tensor network-based approach.
Wait, so they've actually built a quantum computer that can recognize images?
It's still early days, but the initial results are super promising. They focused on classifying simple images like handwritten digits or basic shapes, but the fact that they could do it on real quantum hardware is a huge step forward.
It's like taking a theoretical concept and turning it into a working prototype. It proves that these models can actually do what we hope they can.
It really does, and it's not just about image classification. There have been exciting developments in other areas, like preparing quantum states and generative modeling.
Generative modeling, that's where a computer learns to create new data, like composing music or generating realistic images, right?
Exactly. And in the quantum world, generative modeling could be used to design new molecules with special properties or to simulate complex quantum systems that we can't study directly.
It's mind-blowing to think that we could one day have quantum computers that are not just processing information, but actually creating new things and helping us understand the universe on a deeper level.
It's a truly exciting idea. But like with any new technology, we need to be aware of the challenges ahead.
What are some of the biggest challenges facing QTNML right now?
Well, one of the biggest hurdles is scaling these models up to handle more complex problems. The quantum computers we have today are still pretty limited when it comes to the number of qubits they have and how long they can keep those qubits stable, what we call quantum coherence.
So we need bigger and better quantum computers to really unlock the full potential of QTNML.
That's right. And we need to come up with new algorithms and techniques that are more efficient and can deal with errors better.
So it sounds like there's still a lot of work ahead, but it's really impressive what's been achieved so far.
It really is. And the pace of innovation is incredible. I am confident that we'll see even more groundbreaking discoveries in the coming years.
This has been a fascinating deep dive into the world of tensor networks and quantum machine learning. Thank you so much for sharing your knowledge and enthusiasm for this incredible field.
It's been my pleasure.
So as we wrap up our deep dive, what are some key takeaways for our listeners? What's the big picture here?
I think the most important thing to remember is that tensor networks are a powerful and flexible tool that connects classical and quantum computing. They offer a new way to represent and process information, and they have the potential to completely change the way we solve problems and understand the world.
It's still a young field, but the possibilities are mind-blowing. We've seen how QTNML could revolutionize healthcare, material science, and so many other areas. It's definitely something to keep an eye on.
Absolutely. I encourage everyone to explore this fascinating field. The quantum future is closer than we think.
Thank you for joining us on the Deep Dive. We'll be back soon with another exploration into the cutting edge of science and technology. Until then, keep exploring and stay curious.